Welcome to Efiwe, excellence without stress.
So circular motion, the one we're talking about were linear motion in a straight line. Circular motion is the motion of a body following a circular path. We can see this diagram now, following a circular path. Circular motion is the motion of a body following a circular path. Uniform circular motion is a specific type of circular motion in which the motion of the body following a circular path is at constant speed. I know we've explained that the speed is constant. That is the time it takes for it to change each distance per time is what is constant. So uniform circular motion is a specific type of circular motion in which the motion of the body following a circular path is at constant speed. The body has a fixed central point and remain equidistant from it at any given position. So a constant point. Look at it now. You can see the velocity now equal. That's what is called what? The body is fixed, and that's what is called the uniform circular motion. This is the direction. You can see the velocity, and this is the acceleration, So circular motion is not rotational motion. Both are types of motion under the curvilinear motion. Motion of an object in a curve about a fixed point. That is the curvilinear motion. Rotational motion is a type of motion in which a body rotates about its own axis. And circular motion is a type of motion where a body moves in a circle. That's the difference between circular motion. A body just moving in a circle is a circular motion, but rotational motion is a type of motion in which a body rotates about its own axis. It has an axis and it is rotating about it, and that is what is called the rotational motion. When an object goes around in a circle, the description of its motion becomes interesting in many ways. To better understand the circular motion, let's look at an example. Suppose you have a ball attached to a string and you move it constantly in a circular motion. What are the things we observe? The speed of the ball is constant. Yes, which means the magnitude of the velocity remains constant. The speed, when you start swinging it, you attach the ball to a string and you start swinging it. What do we notice? One, the magnitude of the velocity remains constant around that circular path as you continue to move in that continuous path and that continuous velocity. Don't forget that the magnitude of velocity is speed. At every point of its motion, the ball changes its direction and the velocity is observed to be tangential to the direction of motion. Tangent to the direction of motion. For circular motion, the speed of the object is constant in magnitude. That is size. Magnitude is size. That is for circular motion. Don't forget that. That is so important. The speed of the object is constant. It doesn't change. But its direction is changing in a uniform manner. Its direction, look at it. The direction is changing in a uniform manner. This is the direction changing. But the speed is constant. So don't forget that your acceleration is what? V over T. That is velocity over time. Velocity over time. But now that we have a circular motion, you know that for a circle we have the diameter and half of it is the radius. We have this as r. So what is now going to be our acceleration? Our acceleration, definitely acceleration is velocity divided by time. Velocity divided by acceleration is velocity divided by time. So for a circular motion, our acceleration is the velocity squared divided by the radius of the circle, because we're talking about a circular motion. So for a circular motion, acceleration is what? Velocity squared divided by what? R, where V is the uniform speed and R, this is the R, is the radius of the path. And also recall too that F is equals to ma. Yes, F is equals to mass times acceleration. From that we can get something. Since we know that F is equals to ma, if I put my A here, what is that? I'm going to have another this which is called the what? Ft, which is F is equals to m multiplied by v square over r for a circular motion. For a circular motion, I'm sure we understand what we are trying to say. We started from acceleration. Acceleration is the change in velocity over time. But for a circular motion, acceleration is given as v square divided by r. That is the velocity divided by the radius of the circular path, and that's what we can see here. So, and don't forget that F is equals to ma. That is mass times acceleration. So putting your A into F, right? Let's do that. Putting, sorry. So putting your F, okay, we said that for a circular motion, we have ideally our acceleration is velocity over time. But for a circular motion, acceleration is the velocity square divided by r. And recall that our F is equals to what? ma. So putting a here, so we are going to have that our F is equals to mv square over r, mv square over r for a circular motion. For a circular motion, and that's what we have here. So ft, so centripetal force is defined as the inward force required to keep an object moving with a constant speed in a circular path. So that is the force that keeps that body to continue to move in a constant speed as you are rolling that ball or the swing, and you use your hand to be rolling it. That force, it is an inward force. It's an inward force that is required to keep an object moving with a constant speed in a circular path, and that is what is called the centripetal force. The centripetal force is defined as that force. Centripetal force is defined as that inward force required to keep an object moving with a constant speed in a circular path, and it is given as Ft is equals to mv squared divided by r, and we have discovered how we derived that formula. M is the mass of the object moving with a uniform velocity according to Newton's third law. Don't forget, we are going to do that, or we've done that we are going to do that soon. According to Newton's third law, action and reaction are equal and opposite. It's just like when someone pushes you and you push the person back. The action, someone's action towards you will determine how you will react to the person. If someone is always harsh towards you, you will not be happy. So action and reaction are equal and opposite. So if a force is trying to keep the object to continue to maintain constant velocity in a circular path, another force, an outward force too, must be working with that body according to Newton's law. So according to Newton's third law, action and reaction are equal and opposite. So since a centripetal force must be applied to a body to keep it moving in a circular path, there must be another equal and oppositely directed force, and that force is known as the centrifugal force. So basically, centrifugal force is just working opposite what centripetal force is. Centripetal force is the inward force required to keep an object moving with a constant speed in a circular path, while centripetal force is just the opposite, is acting opposite of the centripetal force. So the differences between them: centripetal force is the force required to provide centripetal acceleration. I'm sure we got that. You know, the centripetal acceleration was A is equals to v squared divided by r to a particle, so that it moves in a circular path. So that is what the centripetal force does. It's that force required to provide centripetal acceleration. It provides, see, this is the centripetal acceleration here, v squared divided by r, v squared divided by r. So centripetal force is the force required to provide centripetal acceleration to a particle so that it moves in a circular path. So that is centripetal force. While the centrifugal tendency of the particle in its accelerated non-inertial frame of reference is explained by assuming a centrifugal force is acting on it. It's just the opposite force. Look at it now. Look at the centripetal force. ensuring that this object is moving with constant velocity. That is the centripetal force. Centrifugal force is acting opposite it. You can see the direction. Centripetal force ensuring that that body maintains a constant velocity. Then this is the centrifugal force. That's the centrifugal force. At every instant, it is directed radially towards the center of the circular path. That is the centripetal force. But this one, at every instant, is directed radially away from the center. That is the centrifugal force. It is a real force arising from gravitational or electromagnetic interaction between matter. This is just a pseudo force. This is the effect of the acceleration on the reference frame of the revolving particle, and that's the difference between centripetal and centrifugal. Centrifugal is the opposite force acting on the body that is moving in a circular path, so that is it. And don't forget your velocity, and don't forget how we derived this formula, that m is equals to v squared r, and don't forget v itself is equals to omega r. V is omega r because of the fact that it is in a circular path. And you can get it also that F is equals to m omega r squared. You know, one r is going to divide one r, so your F can also be what? Mass multiplied by omega squared, which is the angular velocity, multiplied by r, and you will get your formula. And see, that's what we have here, mv squared over r, which is the centripetal force. So let's proceed. Angular velocity, speed and velocity. So when you say angle, you should know that you're going to be having something called theta. This is a circle. You remember that a circle is 360 degrees. So when this thing is moving in a circle, definitely it's going to have an angle. So angular velocity of motion is given by theta divided by time. So don't forget that your angular velocity, that is the velocity of a body that is moving in a circular path, is what? Theta divided by 2. So angular velocity omega is defined as the angle turned through, the angle this particular body is rotating through, divided by the what? Elapsed time. Recall also that velocity is this, just our normal velocity, displacement over time. So for a circular motion, our s will not just be distance, it's going to be called the length of the arc. It's this arc, you can see it here. This is it. This is our s here. This is our s, the length of this arc. The length of the arc is going to be our distance. It's going to be our s. So don't forget, your theta is equals to what? Your omega is theta over t. So your s is equal to what? Your velocity now is equals to s over t, and theta now is equals to s divided by the r. You can see the theta here. This is the theta. Theta is equals to this distance divided by the what? Divided by the r. That is it. Theta, which is the angle, is equals to s, which is the length of the arc, divided by r, which is the what? Which is the radius. That is how to get your angle. That is how to get your theta. I know you can put it into this place also. If you put your theta into this equation, you know what that is going to give to you. So that is how to derive your theta. And you know that s itself is v change in theta. I'm sure you understand that s is like a distance, right? If s is distance, what is the formula for distance? Distance is velocity times time, and that is how we got this formula. So let's try to do that. We have that. This is what we have. Sorry, this thing is hanging. Okay, so we have our omega. Sorry. Okay, don't forget you have your omega to be theta over t. I don't know why this thing is hanging. We have our omega to be equals to theta over t. So having your omega to be theta over t, your velocity normally is s over t, distance over time. And you have that s, that theta, which is this theta, is equals to s, which is the length of the arc over r. But your distance, so you have that theta is equals to s over r. where s is acting as the what, the length of the arc. Don't forget, sorry, small r, don't forget that velocity is equals to change in distance over what, over time. So if I want to make this my distance, if I want to make distance the subject of formula, what is it going to be? Distance will be equals to what? Velocity times time, right? So that is how we have it as v change in theta divided by r. That can also give you your angle. V change in theta, change in time, in t, the elapsed time, over what? Over r. And that was what we had here. That was what we had here. That our theta is s over r. Don't forget what your s is. It's the distance, is the radius. Sorry, it's not the radius, it's the length of the arc. This is the arc. There from here to here is the length of the arc divided by the radius. And we know that s is like a distance. V change in theta is the formula for getting distance divided by r. And we have all of that. So the radian, what is the radian? Radian is defined as the angle of angle subtended by the arc of a circle whose length is equal to the radius of the same circle. That's the radian. So v, as we already know, is equals to s over t, which is distance over time, right? And don't forget, what is our s? Our s is what? R theta divided by t. Our s is r theta divided by t, which we've gotten from here. You can see it from here. If you make s the subject of formula here now, what is s? S is r theta, right? And that is just the s. Then t will be remaining. So don't forget, theta over t is w, is your omega, which is the angular velocity. And this gives us the relationship between linear velocity and what? And the angular velocity. Let's state that again. We have angular velocity here, right? To be theta over t, right? And don't forget, your normal linear velocity is distance over time. If I put the two of them together, s from here now, when we try to get this, our s is r theta. We put the r theta here divided by the t, right? So if s is equals to r, if v is equals to r theta over 2, this theta over t is what? Our angular velocity. So v is related to the angular velocity. Linear velocity is related to the angular velocity by the r, which is the radius, multiplied by the what? Angular velocity. V is linear velocity is equals to radius multiplied by the angular velocity. So what they are trying to tell us that when we know the angular velocity and we know the radius, we can know the linear velocity. So let's check this example very quickly. A bird flies in a horizontal circle with an angular speed. So we have our angular speed. Don't forget that our angular speed is the same thing as our angular velocity, as 5.25 rads. So look at this yourself. Even if you cannot remember your what's it called, your formula, anytime you see rads per second, you know that rad is for angle. So that's definitely theta divided by time. So angular speed of what? 5.25 rads per second, and radius of 650 meters. Calculate the linear speed. Wow, you know, we've talked about the relationship between the two. We talked about the relationship between the angular velocity and the linear speed, and the angular velocity and the linear speed. So what are we going to do? Don't forget, we have that v is equals to omega r. I'm sure you remember how we got that from our previous slide. This is it here, how we got that, how we related them. This is equals to s over t, and we know from here s is equals to r theta over t. So putting this together, theta over t is our omega. That is why we have rw. So this v is equals to r omega is the relationship. Linear velocity is equals to radius multiplied by the angular velocity. And that was what we did here. So look at it now. It's easily explained. You have your omega as 5.25 rads per second. You have r, which is the radius, at 650 meters. So what are we going to do? How can we get the linear speed v? So the linear speed v is just the omega in rads per second multiplied by the radius, and we got it as what? 3,412.5 meters per second. So easy, right? Yes, so easy. We have gotten the relationship between the two. So this is the what? Linear velocity, and the linear velocity is the angular velocity multiplied by the what? The radius, by the radius. So the next question says the frequency of the blade flying in a complete circle. You already know that omega which is the angular speed, is also 2 pi f. 2 pi because of the angle, don't forget that, 2 pi f. So if you make f the subject of formula, it's going to be our omega divided by 2 pi, and that's 5.25 divided by 2 pi. Your pi is 3.14. Then if you do the division, you're going to get the formula of your frequency of the bed. The frequency, when you say something is frequent, you say, you always come into my house so frequently. What does that mean? You come regularly. So frequency is how something occurs. So they said a bird flies in a horizontal circle, and they gave us the angular speed, and this is the speed it's traveling. You know that speed is constant. And I said, how fast? What is the frequency? So for each time the bird is traveling at 0.836 hertz. That's the frequency of how fast it's traveling, because frequency is related to period. F is equals to 1 over t, and t is equals to what? 1 over f. So that is that about that. I'm sure we understand what we are talking about here. We've gotten the relationship, we've explained everything. So, and this is just continuation of all the formula. T, which is period, is related to frequency. T is equals to 1 over f. Well, if you have your frequency, you can get your period. If you have your period, you can get your frequency. And this is what we used just now. Our omega, which is the angular speed, is equals to 2 pi f. How did they get this formula? Just from here. 1 over t is equals to f. So if it's just as I'm saying 2 pi multiplied by 1 over t, and I know that 1 over t itself is what? F. So that was how we got what? This formula. This is just explaining, this is the relationship between the angular velocity and the radiance. So look at, in uniform circular motion, the object in one revolution moves 2 pi r in t seconds. 2 pi r in t seconds. So a circular motion is described in terms of period t. Don't forget your t is equals to what? 2 pi r over v, and these are just different formulas to understand circular motion. So now we want to go to periodic motion. Periodic motion, the motion of an object that repeats its path. This is just a kind of summary of what, because we're going to do simple harmonic motion, a to and fro motion. So the motion of an object that repeats its path regularly after equal interval of time, repeats its path. It continues to move forward and backward, just like someone that they said, okay, be rotating about your point, to just be moving to the front, to the back, to the front, to the back. That is what is called the periodic motion. Look at this now. For example, maybe we attached a string to this wall. We attached a string to this, and we continue. If we pull this thing to the front, it will do what? It will go back. If you push it to the front, it will go back. I'm sure you understand. So periodic motion repeats its motion over the same path. They repeat their motion over the same path, just like the simple pendulum, the earth rotating about the sun. It is continuous. So the motion of an object that repeats its path regularly after equal interval of time is called the periodic motion. It's called the periodic motion. So we can see it now. So over the same circular path, it's repeating it. And this one, a to and fro movement. This is a pendulum. This is the starting point of the pendulum. It will go up, come to this point, go up, come to this point, go up, so at this point, we call this point the rest position, and that is where PE is maximum. PE is maximum at this point and at this point, while at the center, kinetic energy is maximum. Kinetic energy is maximum at this point. So that is periodic motion. So periodic motion is divided into two. We have the oscillatory motion, and we have the ones that are non-oscillatory, but they are periodic because it's continuous. But they are periodic, but they are not what? Oscillatory. So oscillatory motion, periodic motion in which the object moves back and forth. They will always go to the front and come back. Go to the front and come back. Those are what? Oscillatory motion. And they can be divided as the simple harmonic motion or the non-simple harmonic motion, which is called SHM, simple harmonic motion. Then we have the non-oscillatory motion. They are periodic because it's continuous. When you turn on your fan will continue to roll. It is periodic, but it's not oscillatory. Why? Because it's not a to and fro. It is not a toe. When you say oscillatory, it will be going to the front, just like this, like a swing, to the front, to the back, to the front, to the back. That is oscillatory. But these ones are also rotating. They are also periodic because it's continuous, but they are non-oscillatory motion. So look at it now. For oscillatory motion, we have some terms like the time, and we have talked about the time, we have talked about the frequency, right? We already said that the relationship between the time and the frequency is 1 over time. Also, period is also what? 1 over what? Over f. So time, period, and frequency are related like that. F is 1 over t, t is 1 over f. So what is the period? The time taken for the spring to complete one oscillation. If this thing is going like this, one oscillation is not just for it to go to the front, it's for it to go to the front, it's for it to start. If it's starting from here, go to this place and come back. That is how it's completing one oscillation, to the front, to the back, to the front. So that is the time. The time taken for the spring or the pendulum to what? To complete one oscillation is called the period. Why? The number, that's it, frequency, how frequent, frequency. So the number of oscillations that it completes in 1 second is called the frequency. How frequent it's completing one oscillation. 1 second it has completed one oscillation, another second it has completed. So that frequency is what is called the frequency. So the frequency is the number of oscillations like this. One. The number of oscillations it can complete in 1 second is what is called the frequency, and this is the relationship. The unit of frequency is hertz, the unit of period is time. Unit of period is time. So look at it now. When you say t is equals to 4 seconds, what does that mean? It means it takes 4 seconds to complete one oscillation. That is, it went like this. It took it 4 seconds to complete the oscillation, to and fro movement. It took it what? 1 second. So one oscillation, when you say 8 hours, what does it mean? It means in that 1 second, it went, it had 8 oscillations like this, boom, boom, 8 oscillations frequently, and that's the difference. This is just a summary. So now we are going to simple harmonic motion. Simple harmonic motion. What is simple harmonic motion? A simple harmonic motion is defined as a motion in which the restoring force is directly proportional to the displacement of the body from its mean position. The direction of this resting force is always towards the mean position, and the acceleration of the particle executing simple harmonic motion is given as A is equals to minus omega square x. So this is the formula for the acceleration executing what? Simple harmonic motion. Let's take that again. A simple harmonic motion is defined as a motion in which the restoring force, that is, you know that when we are pulling something, when we are pulling the string, like in our previous slide, look at it now. When we are pulling it, something is going to be restoring it back. It's going to be returning it back to where it was. You push it to the front, it will return it back to the front. So that restoring force is directly proportional to the distance. So if this is the distance and this is the force pulling it, they are directly, so it's telling you that the more the force, the more the string will stretch. That is just exactly what that is trying to say. So let's continue. It said simple harmonic motion is defined as a motion in which the restoring force is directly proportional to the displacement of the body from its mean position. The direction of its restoring force is always towards the mean position. The acceleration of a particle executing simple harmonic motion is given by A is equals to minus W square x, where omega is the angular velocity. I'm sure we know that already. Omega is the what? Angular velocity of the particle. Omega is angular velocity of the particle, and we already have that. We already know this already. So simple harmonic, periodic, and oscillation motion. Simple harmonic motion can be described as an oscillatory motion. Why? Because it involves a to and fro. You tied a string to a wall and you put a mass and you are pulling it to and fro. It will go to the front, it will come back, go to the front, come back. So simple harmonic motion can be described. Let me see. I think we have that on our board. So look at it here now. Look at this now. Look at this, our board. This is it now. You attached this is a wall. You attached a mass to the wall. So attaching the mass to the wall, maybe if you pull this mass and you pull it back, there is a force that will always restore it back. And that is how the simple harmonic motion works. And that's why it's called an oscillatory motion. It will go to the front and it will come back, go to the front, come back, go to the front, come back. So look at it now. This is the mass of this birdie, right? So, and it is attached to this wall. You've stretched it. after stretching it, what will happen? This is the main position, right? This is where it is at rest. You pull it to the front. What will happen? It will go back. It will come here, come to the rest position, go to this point, come back to this point, go to the front. And that is what simple harmonic motion is. This is the position it was before. Let's try to draw that. Okay, we have it now. This is your wall. Then you have a string attached to it. And on that string, there is a mass, right? You have a mass. So anytime at this point now, because it's the main position, this is where it is. It is at rest at this point, right? It's at rest at this point. But anytime you now pull it, for example, now maybe you pulled it to this point. You pull it, this is a string. This is simple harmonic motion. It's called simple and in a harmonic, like in a particular point. So this is the mass now. You pulled it. This point is still the what? Main position. You pull it to that. So what will this mass do? It will come to this point, right? And it will go back. At this point, it is going to be very slow. We can say this is the position of rest here. There's a position of rest here. So because if it's coming back here now, what will happen? It will shrink the string. At this point, the mass will shrink it. Okay, now look at it. This is where it was. You pulled it to the front. When it's coming back, it's going to press this thing, and at this point it is fastest. When the string gets to this point, it's having its maximum maximum kinetic energy at this point. But at this point, it's having it's very going to be slowest here, and it's going to be what? Slowest here. And that is the what? Simple harmonic motion, to and fro motion, periodic motion. This string will come to this point, go back. It's just like a child on a swing. When you push the child, this is the starting point of the child. The child will come to this point, come to this area again, go to this point again. And at this point, the child would always rest. There's always a resting position when the child gets to the back before she will launch to the front. So this point now is the slowest part of this motion. While at this point, the center is going to have the maximum motion. And for the simple harmonic motion, the distance between the main position and where it was stretched to is the amplitude. You know, when we talked about waves, amplitude was like the highest displacement. So if I have it like this, remember that this point now is the main position. Just assume that the string is going up and down. This is the main position. So this point, this highest part, is what is called our amplitude. It's called the amplitude. Then what is the period? The time it takes it to complete one oscillation. For this one now, this is the time, because this is where this place started here. So this is where it's going to end. This one and this place is going to be one complete oscillation, and we're going to have what? Our period. Our T, our period. So this is just basically what simple harmonic motion is about. Just the to and fro. And that's what this one was saying, that a simple harmonic motion is defined as a motion in which the restoring force. So there is a force that is always restoring it. Let's go to the board and let's put that there. Okay. There is a force that is always restoring this string back. This is the force here. This point, there is a force here, and this is the distance. So both of them are proportional to each other. So if F is big, if you have a big F, definitely X too will be what? Increase. It means the distance. This one we've done it during elasticity. When I said that if you have a ball and you put a mass, this is a rubber band, you put a mass of 10 kg here, and you have another one, you put a mass of 50 kg. The same type of string, we expect this one to be able to pull. This one was 50 kg. We expect this string, this mass of 50 kg, to pull the string more than the other one. So that is why F, which is the restoring force, is directly proportional to the distance from the main position, from the wall to the main position. So A is given by minus omega square x. That is our A. Our acceleration is given by minus what? Omega square x. Don't forget what your acceleration is. It's just the time rate of the velocity. So simple harmonic motion can be described as an oscillatory motion in which the acceleration of the particle at any position is directly proportional to the displacement. Is directly proportional to the displacement is that x from the mean position. That was what I tried to explain. Mean is the starting point, so it's directly proportional to the distance from the mean position. It is a special case of what? Oscillatory motion. Periodic motion is the motion of an object that repeats its path. We've explained that. An example, a mass attached to an elastic string. That was what I showed you. Motion of the earth around the sun, or motion of the hands of a clock, or motion of a pendulum. So now look at it. Now this was what we were trying to explain the other time when I said that the force, we know that we said simple harmonic motion is a motion that its force, restoring force, is directly proportional to the distance. So look at it now, directly proportional to the distance. The force is directly proportional to the distance. Then we have the what? We have the simple harmonic motion. The simple also, if force is directly proportional to the distance, acceleration also is what? Directly proportional to the distance. That is, look at it now. This string was here now. When it was pulled by this mass, there was a difference, right? The mass, this is the mass of the body. This string was normal here. At this point now, we call this point the main position. We call it the main position. When you stretch it and it goes back, the distance is the x. The F force is what is restoring it back. F is what is restoring it back. So there is a relationship between them. So F is directly proportional to what? The distance. F, the restoring force, is directly proportional to the force. And A also is directly proportional to the what? To the distance also. Don't forget, K is a constant for string. For simple harmonic motion, which is K, we already know our string constant, but the simple harmonic motion is K mass, K per mass. That is K divided by the mass. So that's the constant. The constant is not just the K, because it's totally dependent on the mass. The K is dependent, the constant is dependent on the mass. The constant is dependent on the mass. So if we change this proportionality sign to equals to, and we introduce our constant, we are going to have our acceleration to be equals to minus K over m what? X. Minus K over mx. We're going to have it as minus K over mx. Also, this K over m is given as 4 pi square over t square. So if you put this here, what are you going to have? You're going to have 4 pi square over t square x, and that is the acceleration of a simple harmonic motion. I know it might be looking confusing now, but it is not really confusing. It's just the understanding of it. You have your force, which is restoring this back to its main position. You have the distance. The distance from here to where it's stretched and coming back is what is called the x. Is what is called. So the force, the restoring force, is directly proportional to the what? To the distance. And also the acceleration is also directly proportional to the x. And we got this. Our constant is K over m. K over m. Our constant is K over, which is called the spring constant or the spring stiffness. It is K over m. And this is the value of K over m. So putting this into this equation, we have this. So now can we compare the two? Yes, we can. We have that A is equals to Km over x. And also changing our K over m to be this, we have what? We have it to be what? 4 pi square over t square. We are trying to get our t, because look at it, this is trying to get the equation for t, which is the period of the string, and this is how to get it. So we have your A is equal to minus 4 pi square over t square x. Putting these two together, that is equation 1 at this side, equation 2 at the other side. Don't forget, there is something that is equal to both of them. X, we cancel x, right? So what is left? We have minus k here, minus m is equal to minus 4 pi. The minus sign, we cancel the minus sign also. Yes, the minus sign here, we cancel this minus sign. So what is going to be left? We are going to have K over mx is equals to what? 4 pi square over t square. So if we cross multiply, x has gone, minus has gone. So if we cross multiply, we're going to have t square k is equals to what? 4 pi square m. So taking t square as the surrogate of formula, this will divide your k, right? Then taking the square root, then you have the formula for t, which is the period of a string which undergoes simple harmonic motion. So it is 2 pi divided by m over k, where m is the mass, K is the spring constant or the spring stiffness. I hope you've understood that. So we have gotten our T. So getting our F is going to be very simple because we already understand that T is the inverse of F. So if T is this, F will just be 1 over this, which is be 1 over 2 pi. The one that is down, up, we go down. The one that is up, we do what? We go up. And you can see the relationship between the two of them. They are so much related. Look at T is 2 pi. What is F? 1 over 2 pi. That is no, go down. Exactly. Are you getting that? So this is M over K. What is happening to M, the one for frequency? It is K over M. And this is the frequency of the string. The frequency of the string. Why? This is the period of the string. A string undergoing what? Simple harmonic motion. Very, very simple. Don't forget that it is a to and fro. The restoring force is directly proportional. That was the definition we had of the simple. It said it's defined as a motion in which the restoring force is directly proportional to the displacement of the body from its main position. Displacement is taking you away from where you are displacing. When you say you displace something, this is my rest position, then you are taking me away from my rest position. That is displacement. This was his rest position. Pulling it away from his rest position is what is called the what? The displacement. So if you want to get the T, we already established that F is directly proportional to minus X. A is directly proportional to minus X also. These two are the definition of simple harmonic motion. So we have a constant which is called the spring constant or the constant spring stiffness. It is K over M and it is given by this value. Putting this value into this and doing the right mathematics, which we've explained, we took this to the left side, took this to the right side. We removed the ones that are equal, K minus and minus, we removed it. Then what is left? We have T square K, right, is equal to 5 pi square M. Is that also? Then what did we do? We took this, we divided both sides by K because we only need T square here. So the square root of T square is the square root of 4 pi square M over K. Then T is equal to this. And I already explained how we got our frequency, right? Yeah, because frequency is just the inverse of T. You don't have any issue. 2 pi, it will become 1 over 2 pi. M of root of M over K, it will be K over M. And we are good to go. And we are good to go. We are good to go. So frequency is the inverse of what? Of a period of is the frequency of period. So these are the factors affecting the period and frequency. The period is directly proportional to the square root of the mass. The period is directly proportional to the square root of the mass. Even from here now, we can see that they are on the same line, T and M, but you know that definitely is inversely proportional to the spring constant. So T is directly proportional to the square root of the mass, directly proportional to the square root of the mass. So let's try that. For example, you have the mass to be 4 seconds. Look at the time is 2 seconds, and the time is 2 seconds, right? Look at it again now. When the period is now 16, what happened to the time? The period was now what? 4 seconds. That is the mass. If you have a bigger mass, look at this mass now, 16 kg big, and you have a smaller mass, what will happen to the period? The period of oscillation too will increase. If you have a small mass, it will be faster than when you have what? A bigger mass. Now when you have a bigger mass. So look at this one now. So this one will oscillate faster than this one. That is what this is just trying to say, that this one will oscillate faster than this one. But look at for frequency, 1 over what? 2 seconds, because it's actually 1 over the period, which is this one is 0.5 hertz, while this one is what? 0.25 watts to 0.25 hertz. So what is that telling us? That the frequency of this one is what? Is more than the frequency of this one. The smaller one would be moving faster, frequently than the older one. And that is that about that. So we have gotten the equations for the F, we've gotten the equation for the T. So the simple harmonic motion and angular harmonic motion, these are just the differences, just for you to just know. It's not really something we've derived this. Our acceleration of the particle or the going simple harmonic motion was what? Omega square r minus omega square r, which we've established, right? And so on and so forth. And the angular frequency, which is omega, is W equals to what? K over M rad square. I know you will understand how we got this. Recall that your F is 1 over 2 pi. And you know what your angular frequency is? Your angular frequency is just 2 pi F. So if you remove F and put it in this equation, you are going to get it as this. You are going to get it as this. So we've derived how we got all of these. These are just equations, and we've derived how we got it. So omega is the angular velocity, t is the period, x is the mean position. Don't forget the f is directly proportional to the mean position at some time, and so on and so forth. So properties of oscillation. Displacement x. So we're trying to define all the things that we have. And x of an oscillating system is defined as a distance of an oscillator from its equilibrium position. I tried to explain that. Okay, this is the diagram. Look at it now. This distance from its equilibrium position. This string now moving. This is its equilibrium position. The distance from the equilibrium position is called the x. And the resting point, the restoring force is called the f. Look at it now. This was its equilibrium position. The distance from here to where it is now is called the x. That's the displacement. So displacement of an oscillating system is defined as the distance of an oscillator from its equilibrium position, while amplitude is the maximum displacement. And it's always equal on both sides of an oscillator from its equilibrium position. And that was what I tried to show us here. When I said this point is the amplitude. This is the amplitude of the body, the maximum displacement. It will move, come back to this point, go back. So this place is the amplitude, this place is the amplitude. So that's the amplitude. Angular frequency is defined as the rate of change of angular displacement with respect to time. That is angular frequency. Then we have frequency. We've talked about frequency a lot of time. It's defined as the number of oscillations completed in 1 second. Boom, boom, how fast? Then time is the time taken for you to complete that oscillation. So one complete oscillation is the time taken for the oscillator to pass the equilibrium from one side and back again, going to and fro. So one complete oscillation is the time taken. Maybe this was the main position, to go to the front, come back to that main position, go to the back, go to the front, come back, and don't forget at that center main position is going to be fastest at that point. So one complete oscillation is the time taken for the oscillator to pass the equilibrium from one side and back again fully from the other side. And don't forget what our f is. T is equals to what? 1 over f, and f is equals to what? 1 over t. This is what we are trying. Just saying this is the inverse of it. So what are the relationship between all these quantities? In phase, as one is increasing, the other is increasing, and antiphase, as one is increasing, the other is what? Decreasing. That's just the relationship between the two of them. We already explained that f is directly t is directly proportional to the square root of the mass, and so on and so forth. F is also directly proportional to the displacement minus s. Acceleration also is directly proportional to the a. So force and displacement are in phase. Why are they in phase? Because they are proportional to each other. As the force is increasing, the displacement is increasing. That's what they meant when we're talking about two types of phases. We have the phase, one is increasing, the other is doing the same. While antiphase is when one is increasing, the other is decreasing. So for force and displacement, we've already talked about that. For force and displacement, as one is increasing, what happens to the other one? The other one is increasing also. So they are in phase. So force, acceleration are maximum when displacement is maximum. We've already achieved we already established that f is directly proportional to x minus x, and also a is also directly proportional to what? Minus x. What about the amplitude? Amplitude and energy are in phase. We already know that energy is just the maximum displacement. When we were explaining elasticity, then we said if a child is to swing, is to throw a string, and is to displace a string, or an adult is to displace a string, we know that the adult will have more amplitude. The adult string will have more amplitude. Why will the adult string have more amplitude? The adult string will have more amplitude because of energy. So amplitude and energy are in phase. What does that mean? The more the energy, the more the amplitude. The more the energy, the more the amplitude. The velocity and energy and displacement are not in phase. That is, energy or velocity is maximum when displacement is 0 or minimum. Don't forget that energy or velocity is maximum when displacement is 0 or what? Or minimum. So they are not at all in phase. So what are the things to note? These formulas are because simple harmonic motion, a lot of things. The velocity of a body in simple harmonic motion at a distance x From the equilibrium position, A is the amplitude. Don't forget that. S square is the mean position. So for me to know the velocity, it's the angular velocity multiplied by the what? Square of the amplitude minus the what? The mean position. So the velocity of a body, you know that this is the linear velocity. Velocity of a body is in SHM at a distance x from the equilibrium position is given as this. So if you are asked to look for the velocity, you will multiply what? The angular velocity by the what? Amplitude square minus the x square. Sometimes the x can be 0 from if it's at rest at the mean position. If it has not been stretched, the x will be 0. But when stretched, you have to know the value. So velocity and kinetic energy is maximum at equilibrium position. Yes, that was what I was trying to tell you. At this point of the string, this point, okay, it was, I drew it on the board. I think I drew it on the board. Okay, let's check our board then. Okay, that's what I was saying. At this point, this was where the body was at rest. Nothing as it has not been displaced. Before we now displaced it to the front, we pushed it. You know, this was where it was initially. Before we now pushed it to the front. So at this point, it has the maximum. Let me redraw that so we can understand what I'm saying. So we have our string. This is the wall, right? This is the wall. Then we have it that. Okay, we have small, then we have the mass here. This is the mass, right? We've not displaced it here. So later we stretched it. This point is the mean position, right? So we know when we stretched it, this place has increased, right? So what is happening here again? There's a force that must actually be restoring it. This is the x. From the mean position, you know, this was the mean position. From here, which was here, to this point now is what we call our x. From where it was to this point is the mean position. The mean position where it was before to where it's now stretched. Here now is the amplitude. To this side, it's going to stretch to this side also. Another amplitude. Are we getting that now? So there is a force now that must be restoring it back. As we are pushing it, this force will be returning it back to its main position, and there will be a time when it will look like this, when it will be so, it will shrink so much to this point. So look at the body now. This was this main position. So at this main position, velocity is maximum. Kinetic energy too is what? Maximum. Don't forget that K is half mv squared. So definitely, if V is maximum at that point, the kinetic energy too is maximum at the main position. So as this body is moving, now supposing it was like a swing, when it gets to this point here is where it's going to have its maximum kinetic energy. At this point, it's going to be the slowest point. Just like when you are on a swing, when you move to the back, you will stop before you now come back. This point is the maximum speed. Come to the front again, then you have the slowest part also. So that's what that was trying to tell us. That was what that statement was trying to explain to us, that velocity and kinetic energy is maximum at equilibrium position where the displacement equals 0. You know, it has not moved. It has not moved at that point. So the displacement. So what will happen to V max then? X squared will be 0. Then V maximum is just the omega multiplied by the amplitude, because x is 0. It has not moved. This x is just from the mean position to where it is now. The displacement is what is called x displacement. That is where you were. I'm displacing you. Maybe, okay, you are here before. Oh yeah, I want to displace you from this your position. That is displacement. So when V is maximum, our formula is what? Omega A. Velocity and kinetic energy is minimum or 0 at the extreme, yes, position. And I've explained that kinetic energy is minimum, very small. At this point, that was what I was saying. This is slowest here, fastest at the main position, which is this center, and also slowest here. So kinetic energy is either 0 here or what? Minimum, but it is maximum at the center. So this is the string here. At this point, the kinetic energy is maximum. When you push it, the kinetic energy is what? Is maximum. So velocity and kinetic energy is minimum or 0 at the extreme position. That is maximum displacement. The types of simple harmonic motion, we have the linear and we have the angular simple harmonic motion. So we have the angular simple harmonic motion and we have the linear simple harmonic motion. Linear simple harmonic motion is when a particle moves to and fro about a fixed point called the equilibrium position along with a straight line. Then this motion is called linear simple harmonic motion. For example, the spring mass system, the one we explained. So what are the conditions? The restoring force or the acceleration acting on the body should always be, we've already said this countless time, proportional to the displacement of the particle and directed towards the what equilibrium position. So this is another formula. Your angular velocity is 2 pi f. That should be on your head. Then why are we having it as also 2 pi t? Because f is equals to what? 1 over t, right? And that's why we have it as 2 pi over t. So you can use this to get your what? Angular velocity. Then v, what is the relationship between angular velocity, velocity of a body moving in a circular path or undergoing an oscillatory motion, and the linear velocity? We've achieved this, Abby, in the previous sessions, which is v is equals to what? Omega a. Remember how we achieved this? When do we have this? This is v maximum, when the mean position is what? Is 0. That was when we have this. So at the extreme end of the motion, where a is amplitude, v could be given as this, right? Where they explained this, when there's a displacement. But when x is 0, and that's when v is maximum, w is v will be equals to omega what? Square root of a square. So linear acceleration, the rate of change of angular velocity with respect to what? To time. So and that's what is it? We have the acceleration as minus w square x, which we've seen in the previous class. So in the case of a string or spring, angular velocity is given as the square root of k over m. Don't forget this, k over m. This is for angular velocity. If it's not the frequency is just 1 over 2 pi square root of k over m. While the t is just what? 2 pi square root of what? M over k. So simple, so simple. And time is this. That was what I was just trying to say. It's just by introducing the 2 pi. And for the one for f, we just be what? 1 over 2 pi, right? And we are good to go. So in the case of a simple pendulum, time period is given as 2 pi. It is now L over G. In the case of a simple time period is given as this. So note, period of oscillation and frequency of a simple pendulum depends on the length. This is what it's trying to say. The time and the frequency depends on the length. This is for a simple pendulum. A simple pendulum, a type of simple harmonic motion. So it is 2 pi square root of L over G. Why? Because of the length of the motion. Length of the motion is not the mass. You know, for a string connected to a mass, we have what? 2 pi square root of M over K. But this one is square root of L over G, because G is affecting it, acceleration due to gravity. So period of oscillation and frequency of a simple pendulum depends on length and acceleration due to gravity only. Don't forget that. This is what the period depends on for a simple pendulum. For excuse me, for a simple pendulum, thus the period increases when the length increases and acceleration due to gravity decreases. Anytime you see an equation like this, that you should have understood it. The one that is in the same line is directly proportional. The one that is under is inversely. That's why I'm saying t. When t is increasing, the length is increasing. But when the acceleration is decreasing, what will happen to t? T will be increasing, because they are opposite of each other. So the period of a simple okay, let's read this. This is a question. The period of a simple pendulum in moon is greater than on earth. Why? Because period of a simple pendulum is inversely proportional to the acceleration due to to gravity, and on the moon acceleration due to gravity is minimum. So the period of a simple pendulum in moon is greater than that of earth. Is greater than that of earth, because period of a simple pendulum is inversely proportional to acceleration due to gravity. So acceleration due to gravity, that is why the period is greater, because on the moon, very low acceleration due to gravity, very, very small acceleration. But on the earth, we have a big acceleration, and that is why the period of the moon is greater than on the earth. Acceleration due to gravity on the moon is less than acceleration due to gravity on the earth. Yes. So acceleration due to gravity is very small, and since it's inversely proportional, if acceleration is small, what will happen to t? Let's quickly talk about that on our board. We said it on the moon. This is the moon. The moon has very small. We already established that t for a simple pendulum is just dependent on what? The length, right? divided by what? Acceleration due to gravity. And I've already explained to you that this is telling you that T is directly proportional to L and T is inversely proportional to G. So the question is, on the moon, what happened? On the moon, there's the acceleration due to gravity. The effect of acceleration of gravity on the moon is very small. So if G is small, what will happen to T? T will be big. If G is big, what will happen to T? T will be what? Will be small. And that is what we are trying to explain. That is what we are trying to explain here. That acceleration due to gravity on the moon is less than acceleration due to gravity on the earth, and that is why the period of a simple pendulum in the moon is greater than that on the earth. And these are the formulas. I just put the formulas here together so that you can remember. W is equal to K over M. Don't forget, if it's going to be your frequency, it's just putting 1 over 2 pi and you are good to go, right? You are good to go. And this is it there for the T. The relationship has been explained in all of what we've been talking about. Then the energy of a simple of a motion undergoing simple harmonic motion, the energy is equal to half mv squared. You know that this is kinetic energy. So what is our V? Remember what your V is. Your V is W squared multiplied by the A squared. You can remember that, right? W squared omega squared multiplied by the A squared. So what is our E? Total energy of the simple harmonic system. M is our mass of the oscillator. Omega is the angular frequency, right? And A is the amplitude. And then you can get your what? Your energy. Then this is our example to understand all what we have been saying. A body of mass 20 kg, okay, is suspended from the end of a spring, of a spiral spring, whose force constant is 0.4 Newton per meter. That is K, right? We know the mass of the body as 20 grams. They said is suspended from the end of a spiral spring, whose force is 0.4 Newton per meter. The body is set into simple harmonic motion with amplitude 0.2 meter. Wow. Then calculate the period of the motion. We already know that, right? The period T is just 2 pi divided by omega, and we have it as this 2 pi mass, which is 20 grams, right? And don't forget, you have to convert your 20 to kg, because you know the unit of mass is kilogram. So look at it, the formula 2 pi root m over k, root m over k. So what's happening? We're going to put our mass there, then our k, which is the constant, has been given as 0.4. And can we get our period? Very well, easily, and we have the period. So this is the period that it takes to complete what? One oscillation, 1.4 seconds. So it's as if the string is moving like this in 1.4 seconds. It's going to the front and to the back in 1.4 seconds. Front, back, 1.4 seconds. And that is it. Then what is now the frequency? We know the relationship between frequency and period. The relationship between frequency and period is what? 1 over what? The time of the period. And it gave us this. And that is cool. So the next question is the angular speed. So simple. We already know the angular speed is what? 2 pi f, right? 2 pi f. Then 2 pi multiplied by what? 0.71, because 2 pi is giving 0.71 was the frequency we got it, and we got our answer as what? 4.46 rad per second. 4.56 rad per second, and that is okay. Then the total energy, we've already gotten this. Our total energy, E, is 1 over 2. The K, which is the spring constant, multiplied by the amplitude square, right? And you can get your answer like this, which is 1 over 2 multiplied by 0.4 multiplied by 0.2 square, and we have our answer. So the next question, I said the maximum velocity of the motion. The maximum velocity of the motion. You know, when do we have the maximum velocity of the motion? Don't forget, it is when x is equals to 0. So that would have just given us omega squared minus a, right? It will just give us it, because ideally it's supposed to be a minus x, but we know at this point x is 0, because that is when we can have the maximum velocity. So we put it there as 4.46 squared multiplied by 0.2, and it will give us this. And wow, we are good, and that is all.